Welcome back to Enzymes, Biological Catalysts. This time, we will see how enzymes can alter reaction energetics to catalyze reactions. To get the most out of the videos, I recommend that you watch them in order. This is a reminder that this presentation is Dr. Johnson's intellectual property. In order to understand catalysis, and enzymatic catalysis in particular, we need to have a good understanding of reaction energetics. These are most easily illustrated with a reaction progress diagram. In this diagram, we can see that the substrate and product have different energy contents as indicated by delta G naught. The ratio of the equilibrium concentrations of substrate and product, as we see in the equilibrium constant, is governed by thermodynamics, where delta G naught is minus RT ln of the equilibrium constant. This tells us how favorable the reaction is. The other feature of this diagram is the energy required to reach the transition state, delta G double dagger. Notice that this is different for the forward and reverse directions of the reaction. The activation energy is a kinetic barrier. It determines how quickly the reaction will progress. Finally, you should notice that the rate constant for the reaction has an inverse relationship with the activation energy. The smaller delta G double dagger, the faster the rate of reaction. Catalysts increase the rate of reaction without being consumed or otherwise altered by the reaction. They lower the activation energy of the reaction, but do not affect the equilibrium position. There are three main ways that enzymes can affect the reaction progress to cause catalysis. We'll have a look at these on the next slides. Enzymes bind to their substrates. This event can be used to convert the reactant to a less stable species, for example, by altering the conformation of the substrate. This changes the starting point of the activation energy from substrate to the ES complex. It is useful to point out here that if the enzyme is exactly complementary to the substrate, the ES complex will be more stable than either enzyme or substrate by themselves, and the activation energy from the stabilized ES complex will be even greater than for the unbound substrate. Clearly, this is undesirable for catalysis. This is the main reason why the lock and key theory for substrate binding, originating in an 1894 paper by Emil Fischer, is not considered to be valid. Instead of being complementary to the substrate, enzymes are complementary to the transition state of the reaction. This means that substrate binding results in stabilization of the transition state and has a dramatic effect on the energy required to make the reaction occur. Consider that many of the reactions that occur in your body would need to be heated well over 37 degrees in order to happen at an appreciable rate. However, the enzymes in your body are able to catalyze these same reactions so that they occur rather quickly at 37 degrees. The concept presented here, where the enzyme changes the substrate conformation to be closer to that of the transition state, is known as induced fit. This idea was introduced by Daniel Koshland in the mid-1950s. At first, his idea and paper were rejected because it went against the established lock and key theory. However, after numerous attempts, his paper was published in 1959. A close reading of Emil Fischer's paper, from which the lock and key theory arose, shows that this concept was a comment regarding the selectivity of the enzyme for certain substrates, and was never meant to be taken as literally as it was. Enzymes can also interact with the substrate and intermediates of the reaction, reacting with them. This changes the mechanism of the reaction and is another way to make the reaction faster. So, when an enzyme catalyzes a reaction, it decreases the overall amount of energy required, often using all of the methods we just discussed. You can see this on the reaction progress diagram. The equilibrium positions of the substrate and product have not changed, but the activation energy has been decreased. Because less energy is required, the reaction is faster. You should note the delta G naught prime value. This is the standard transformed free energy that differs from chemical standard state in having a pH of 7 rather than 0. In addition, the amount of magnesium ions may also be different in the biochemical reaction than the corresponding chemical one. Next time, we'll have a look at just how well enzymes can catalyze reactions.